Good day to all. Welcome to the second lecture in the Unit 2. In this lecture, we are going to see about what is the equipotential contours for uniform and non-uniform fields. Before going into the topic, we have seen in the previous video that what is the relation between the electric field and the potential field. So this is the relation we have derived in the last class, that is E vector is equal to minus del into V vector. Here you can see one thing that the E vector is depends upon the square of inversely proportional to the square of the distance, and V vector is inversely proportional to the distance only. It is not inversely proportional to the square of the distance. It is inversely proportional to the distance only. So we can derive the analogy that with the gravitational force on the in the earth on an object. So if you have an object which is coming from the atmosphere to the earth, if that object is located around 6 miles from the earth, and if you compare with that particular object which is coming near to the earth with the distance of 3 miles. So 6 miles and 3 miles are going to be the test case for us. So if you measure the velocity of the particular particle on the 6 miles, then it will be very higher, that is 4 times higher than the particle which is on the 3 miles away from the earth. So that is the thing which we have seen mathematically, that the electric field is going to be inversely proportional to the square of the distance, and potential field is going to be inversely proportional to the distance. So this concept have to be bear in your mind. So depending upon this concept only, we are going to derive the equipotential contours. So for a uniform field, if you are assuming field lines are going to be excited from the right to left, then if you measure the potential across these particular electric fields, we will be having each and every potential points here. So this is the zero potential point, this is the zero potential line, and this is the 10 volt potential line. Then we have measured each and every particular potential lines along this particular path of this E vector. So if you measure that particular E vector along this particular potential along this E vector, then we will be having the E vector as 0.2 volt per mm. What does it means is 1 volt line, that is, this is the distance from this particular one to this particular one. So if you are taking this distance, that 1 volt line with 5 mm apart. Why it is 5 mm apart? Because we will be having the volt which is 1, if it is going to be 1 volt, and this 1 volt after if this is going to be 0 volt and this is going to be 1 volt, then the difference is going to be the 1 volt. So 1 volt which is separated apart 5 mm only. So whenever we are having this particular calculation, that is 1 divided by 5, it is 0.2, which is volt per mm. So that is why we are drawing the potential lines along this particular path of the E vector. So 0, 1. So this distance between these two is 5 mm, and along the E vector we can draw up to 10 volt. So this is the example for an uniform field. So if you are taking any uniform field, we can segregate that particular electric field lines with the potential field lines like this. So we can define the potential field along the electric field lights, like we have done in this example. So in this example, we are having E vector as 0.2 volt per mm. If that E vector is going to be 0.2 volt per mm means then 1 volt line. So the potential difference between these two lines, if it is going to be 1 volt, then these lines are apart from 5 mm. So that is the meaning of this particular equipotential contour. So these contours are potentially equal with each and every partition. So larger potential difference between the 2 points are going to be stronger field. So if you are having the electric field as very stronger, then if you want to find out the potential difference between the 2 points, then it will be larger one. So if the potential difference is larger, then the field will be stronger. So next one is going to be non-uniform fields. So if you're dealing with the non-uniform fields, the non-uniform fields are going to be represented by radial lines. So field lines are radial. So if you are having a point charge Q, then you will be having field radial lines along this particular which is originated from the Q charge. So the radial lines are being diverged from this particular point. So if you are going to measure the voltage, that is the potential along this particular radial lines, then you will be having the contour lines of circle in nature. So if you are having that particular contours in the circular nature, the field lines are more widely separated as the distance increases. So if the distance are being increased, then the separation between these circles are going to be increased. So if you measure the distance, so I have drawn a simple diagram. So if you have radial lines along circle lines along this around this particular charge, they will be very congested in nature. So if you have this particular circle lines apart from this Q, then the distance between these points are going to be increased. So you can also see the distance between these two lines are very greater than between these two lines. So that is the meaning of this line. The field lines are more widely separated as the distance increases. The potential rise is also opposite to the E vector. So here you can see the E vector are going to be non-uniform in nature. So if it is going to be non-uniform in nature, then you can see the potential difference. The potential difference between these two are 2 volt. That is 3 volt minus 5 volt minus 3 volt is 2 volt. 10 volt minus 5 volt is 5 volt. So you can see the distance between these two is larger, but distance between these two is somewhat less. But the potential difference is here only 2 volt, here it is 5 volt. So distance is larger, but the potential difference is lower. Here distance is lower, but the potential difference is higher. So this is how the non-uniform fields are going to be exerted in nature. So the practical example for this spherical charges which is used in the high voltage labs are going to exert these kind of non-uniform fields. So this is what about the equipotential plots. After this, we will be going to see some useful relations. So one of the useful relation is integration of E dot dl is equal to 0. So what does it actually means is this integral is a closed path integral. The electric potential around the closed path is always 0. So why? because the reason is obvious that the path returns to the point where it starts, so that the net work done is going to be zero. So we have seen this particular concept in the previous video itself. I'm again I'm going to say the same thing, that is the work done around a closed path is always going to be zero. Why? Because we are going to travel from to a closed path, but if we are traveling around the closed path means the potential difference is always going to be zero, because we are starting from one point, we are ending at the same point, because it is a closed path or closed circuit. So that is why we are going to have the work done, the net work done is going to be zero. So that's why the closed integration of E dot dl is equal to 0, because the work done is, net work done is 0. Also from this relation, if you take this particular relation, then it is going to be the circulation of the E vector. So because we are taking the line integral along the path of dl across the E vector. So if you are taking the line integral across any vector field, then it is going to be circulation of that particular vector field. So from the Stokes theorem, we know that the circulation of the electric field is going to be equal to the surface integration of the curl of that particular electric field. So from this relation and this relation, we can come to a conclusion that this del cross E is also going to be 0. So del cross E is going to be 0. That what does it means is, del cross E is curl of E. So if you are taking a curl of an electric field, it is always going to be 0. This can also be proved from fact that E has a scalar potential gradient. That is, E is an electric field, and del V, that is E vector, is equal to del V, which is the relation which we got derived in the previous video. That is, this particular electric field is going to be having a scalar gradient. That scalar gradient is going to be the potential gradient. So this electric field has a scalar field, means scalar gradient means then its curl is going to be 0. How? That is, del cross E, if you are taking, if you substitute del V, that is the gradient of V for this electric field, then we will be having del cross del V, that is the del cross gradient of V. So always a gradient, if you for a gradient, if you are taking curl, it is always going to be 0. This is an important identity which we have derived in the first unit itself. So I have given this in your online class itself. In the previous online class itself, I have given some of the vector identities. You can refer to that particular video, or you can refer to the material which we have given to you. So in that material, we have given a vector identity that a curl of a gradient is always going to be 0. So we can prove in the either way. So we can prove this identity with the help of Stokes theorem and also from the vector identity. Next we are going to see what is the utilization factor. Field utilization factor is going to be defined by a ratio called as mean electric field in a sphere. So if you are going to measure electric field or utilization of a particular electric charges which are available in a sphere, if you want to find out what is the utilization for that particular charge distribution, from that charge distribution we will be having the field. So if we want to find out what is the utilization factor for that particular field, means we can find out the utilization factor for that particular field from the mean electric field in the particular sphere divided by the maximum electric field which is exerted from that particular sphere, then if you are making ratio between those two values, then we will be having what is the utilization factor. So this is all about this video. Thank you.